Hi. Today we'll talk about conservative and non-conservative forces in Chapter 7, Work and Energy. From the title you can tell that there are two types of forces. We have forces, we call them conservative forces, and the other type, non-conservative forces. So we have to distinguish between two types of forces. Now, so far we dealt with many forces, yeah? So I list them, the forces we dealt with, and then we decide which one is conservative, which one is non-conservative. So the first force of gravity, F sub g. Yes? The other force, maybe normal force, okay. Friction force. Yeah? Tension force, F sub t. Applied forces in general, F sub A, yeah? Push, pull, yeah? Anything else? There's one more. Spring force. Okay? So these are the forces we dealt with so far, yeah? Gravity, normal, friction, tension, applied forces in general, spring force. Which means now, of course, this is the list for mechanical parts of physics. When you have electricity, you have other forces as well, yeah? Electrical force. Now, it means some of these forces are conservative, some are non-conservative. Of course, I'll explain what is conservative and not. But as a guess, which one you think is conservative? Fg, yes? F sub g. So F sub g, gravity force, is a conservative. What else is conservative? F, T, no. Tension forces, no. Normal force. Friction, no. Spring force, Fs. So gravity force and spring force, both of them are what? Conservative forces. Which means the rest? Just remember these two. Fg and Fs. Gravity force, spring force are conservative forces. The rest are non-conservative forces. Of course, like friction force and applied forces, yeah? Because we deal with friction force and applied forces a lot. Now, we want to understand what does it mean a conservative force or non-conservative force. The word conservative comes from conservation, yes? Conservation. If a person conservative means he's protective, yeah? He doesn't like to change, or she doesn't like to change. They are not liberal, so they don't give and take, yeah? They keep what they have. Here, think of energy. Energy conservation, yes? The word conservative here means there is no change. What you have, you keep it, yes? You don't like to give or take, conservative. This is the meaning of word conservative here. But here we're talking about forces. So these forces are conservative. Why they are conservative? It's because to do with the energy they comes out of this. Now, if you have forces and you want to test if the force is conservative or not, I'll give you two characteristics of conservative forces. And then we discuss these one by one. So how do I know the force is conservative? These are the conditions. So you say conservative forces. I'll write it down. You can write with me to save time. You have conservative forces if you have number one fulfilled. Number one says the work done by a conservative force on a particle moving between 2 points is independent of the path taken by the particle. So this is the first condition. I read it. The work done by a conservative force on a particle moving between 2 points is independent of the path taken by the particle. That's the first condition to have a conservative force. Second, the second condition, the work done by a conservative force on a particle moving through a closed path is 0. The work done by a conservative force on a particle moving through a closed path is 0. Done? Okay, now let's discuss this. These are the conditions to judge a force, if the force is conservative or not. If you have a conservative force, it means when you use this force to do work for you, the work done by the force, to take the object between 2 points, start, finish point, you will find that the work done by this force does not depend on the path. Any path you take, it still gives you the same answer between start and finish. That's what it means now. In the drawing, let's say I have a force acting on this object here. What is the force? F, conservative. A conservative force. Initially acting on the object which is here, yes? Now, when this force acts on the object, there is a displacement. There is work done by this force. Suppose that finally it's here. When you apply the force, the object moves from initial position, final position, yeah? Now, if this force is conservative, you'll find the work done by this force does not depend on the path between I and F, which means if you calculate the work done by this force on this path, path number 1, or in this path, path number 2, or in this path, path number 3, any path you take between initial and final, you'll find the answer is the same. So W, F conservative from I to F here does not give you a different answer if you take it for path 1 or path 2 or path 3. W conservative has the same value. One value, yeah? So this is when the force is what? Conservative. So if you have a conservative force and you apply it to do work between an initial and final position, you'll find the work done does not depend on the path. So you can go on this path, you get the same answer if you go on the blue or on the red. Now, where is the beauty of this law? If I ask you to calculate the work done on this path, on the green, is it easy? No. Work needs force, displacement, cosine, the angle between them. And you can see here, it keeps changing the direction. So it's not easy to calculate the work on path number 1. Path number 2? Same, hard. But path number 3? Because you have the force, displacement, and the angle between them. So which path you choose to answer the question? Third one. But it's the same answer if you choose the first one and second one. So whenever you want to calculate work and you know the force used is conservative, choose the easiest path to calculate, because the answer will be the same. This is useful technique, yeah? Because it's conservative. Conservative doesn't depend on the path. It just depends on initial and final position. All right? But what if the force is non-conservative? It depends on the path. So the work on 1 is not equal to the work on 2, work on 3. Yeah? Clear? That's first condition. If I have a conservative force, again, look, it's to do with the work done by the force, not the force itself. The work done by a conservative force moving through, this time, not from one point to another, no. Closed path, which means you start at a point and back to closed. How much is the work? Always 0. If the force is conservative. But if the force is non-conservative, not equal to 0. So again, this is a way to test. If I give you a force and I say, is this force conservative or not? What you do? Use it to do work for you in a closed and calculate. If the answer is 0, you say, yes, this is conservative force. If the answer is not 0, positive, negative, force is non-conservative. So this second one, it means this. If I start at initial point here, apply a force conservative, but I apply it in such a way it does work for me back to the same point, final, closed path. You start and back to the same point, yeah? In any shape you like, doesn't matter, closed. So how much is the work done here by F? If F is what? Conservative. But if S is not conservative, no. Not. All right, so now do you understand what does mean conservative and non-conservative forces? Right. Now let's apply these on what we know, the forces. So I'll take an example of a conservative force and an example of non-conservative. Like I'll take example of gravity force, which is conservative, and I take the example of non-conservative friction force, and I apply these. Let's say we have an inclined surface, theta, and initially the object is here, and we pushed it up, finally it's here, final position. Now what's the question? calculate the work done by gravity force here only. What is the work of Fg from initial to final position? Okay? Now, to calculate work, what do you need? Force, displacement, and the angle between them. Right. Let me give you numbers here. So, calculation. Let's say in this question, Fg value is 10 Newton. The mg completely 10 Newton. And let's say from I to F, this distance L, 10 meters. And let's say theta here, 30 degrees. And the question is find the work done by gravity force. Which way is the gravity force? Down. Perpendicular on the ground, yes? Of course, here it's a little bit hard, so I'll draw one in the middle so you can see it, yeah? Fg. Which way is the displacement? Parallel to the surface, yeah? Delta R. What's the angle between them? Is it theta? No. Alpha. No, it's just, I'm saying going from initial to final. It's going up. I to F. Now, how much is WFG from I to F? Magnitude of Fg, magnitude of the displacement, cosine the angle between them. Yes, agree? How much is Fg? 10. How much is delta R? 10. How much is alpha? 90 plus theta. When you go up, it's 90 plus. So alpha here, 90 plus theta, which is 120 degrees, yeah? Now, calculate how much is it. Definitely is negative. Negative 50, because cosine 120 minus negative 50 joules. Right. Force of gravity. It's a conservative force or non-conservative? Which means this force, its work doesn't depend on the path. Any path you take to go from I to F, it still gives you minus 50, yes? What's the proof? We'll prove it now. Now, think of this as path number 1. You went straight from I to F. Now I'll choose another path. But this time I number them. I to F, I say I is number 1. This point here, number 2. And this is number 3. So it means now I'm moving, instead of taking the box on the incline, no, I'll take it horizontally, this way. And then I take it vertically here. Did I reach final or not? Yeah. But different path. Now, the theory tells me if I calculate the work on 1, 2, 3, the answer must be? Let's see if it's minus 50 or not. What is the work from 1 to 3? It's the same as work from 1 to 2 plus work from 2 to 3. You add them, yeah? Divide. Now, let's say work from 1 to 2. What do you need? Force, displacement, and cosine 90. So here I have FG delta x cosine gamma. Listen here. Where is FG? Where is the box here? Not this way. Now it's moving this way. So I'll draw one here for you. Where is FG? Which way is going? What's the angle? So gamma is 90. Cosine 90. So how much is the work done from 1 to 2? Now 2 to 3. 2 to 3. Now 2 to 3, if I draw the mass here, somewhere in the middle. Where is FG? Which way are you going? What's the angle between them? 180. So here I have FG. What shall I call this now from here to there? Delta Y. This is L. This one delta X, and here we'll have delta Y. Cosine what? 180. Now delta Y means the distance from 2 to 3. Is it given or I can calculate it?
We can calculate it.
Calculate it. This angle is 30 and this side is 10. So on this triangle, 30 and 10, how much is this? Using sine or cosine? Sine, opposite, yeah? So sine 30, delta Y over 10. So delta Y is 5. Because sine is 30 is half. So here what you put? FG is 10. Delta Y is 5, and this is minus 1. What's the final answer? June. Did we get the same answer or not?
Yeah.
So it doesn't depend on the path. Now, you should learn something now, which you can use it always for force of gravity work. Whenever you want to calculate the force of gravity, do you have to bother about motion horizontally? Because when the object moves horizontally, Fg and delta x at 90, 0. So what is counted always? What you have vertical. So if I say what is work of gravity from 1 to 2, think of it as from 1 to 3, sorry. From 1 to, you just need the height. Anything horizontal is not counted, 0. But be careful. Sometimes you go up, sometimes you come. If you come down, the angle is 0. Because Fg down, delta Y or delta R is down. This is the only difference, yeah? So for work of gravity, when you go up, negative. When you come down, positive, because you go with the gravity. You got it now? This is how you test a conservative force. Now let's take an example of non-conservative force, which is a friction, and let's see if it depends on the path or not. What do you know? It doesn't, it depends or doesn't? It depends on the path, which means it doesn't give you the same answer for different paths. Right. Let's think of what this chair. Here I have a chair at this point, initially here, and finally I'll take it to the door. Huh? Now I draw it here. Initially it's here, and finally by the door here. And there is a friction on the floor, yeah? Now, what's the question here? What is the work done by friction, which is non-conservative, yes? To go from I to F, but using different paths. First path, straight, yes? So I go from I to F straight, path number 1. Now let's say from here to there, 5 meters. So this path is called L, 5 meters. And let's say the force of friction, when you calculate it, there's no need to go into details, give it a value. Let's say FR is, again, let's say 10 Newton. Because Fr, you can find it by mu and n here doesn't change, yes? N equal Fg. And mu doesn't change, the same floor. So we didn't change the floor. Right. Now, first case, I'll take the chair from here straight. Yes? How much is the work done by friction? Path number 1. W friction from I to F. You need the friction force, displacement, cosine what? Cosine what? Friction force, 180, always, always. So the work of friction is always negative. Now what is Fr? 10. Delta R by minus 1, it's minus 50 joules. Yes? This is in which path? Straight. Now I'll choose another path. The chair was here, yes? I want to go to the door, but I'll move the chair from this point 1 to point 2 here. And from here to there is 2 meters, so I'll draw it here. You started here, finished there, 2 meters, yes? Then from here to the rubbish bin, 3 meters. Then, from here, straight like that, 2 meters. And then from here to the final, maybe 3 meters as well. Yes, you take it from here to the final. Now, this is path number 2, the red one. Path number 2. Now, what is the work done by friction on path number 2? Which means WFR, path number 2. Of course, I can divide it to works, yeah? So, first part, from here to there. How much is the work of friction? Friction force, displacement, cosine, 180. So the first part is FR delta x1 cosine 180 plus second FR delta x2 cosine 180 plus FR delta x3 cosine 180 plus FR delta x4 cosine 180. How much is FR? 10. Always, yes? So what is the first one? 10 by 2. So we have 10 by 2 by minus 1. This is the first one. Plus 10 by 3 minus 1. 4, third, plus 10 by 2 plus 10 by 3. All right? What's the total here? Minus 20. Here, minus 30. Minus 20. Minus, what's the total? This is the work of friction on path number? Same answer or different? Because it's non-conservative. When you choose a different path to go to the final position, the work done by the force, which is non-conservative, is 0. Sorry, it's a different value. All right, I hope I convinced you now why friction is non-conservative. Now remember, applied forces like friction force, non-conservative. Think of this as not a friction. You push this way, yes? On this path, and push this way, and push this way, and push this way. Will you get the same work if you push it straight to the end? So it's non-conservative. Applied forces are non-conservative. Now, normal force. There is no need to calculate the work of normal force because it's always, so we don't talk about it at all. Even if you say conservative, it doesn't, yeah? Tension force. Now, tension force depends. If you say one cable, like I'm pulling the chair with a cable, yeah? When you pull it with a cable, not with my hand. What's the difference between this and an applied force? Same, yeah? So it's non-conservative. But when you have tension between two masses, like this, let's say you have this question. M1, M2, okay? Do we have tension force here or not? Yes. Right. If you want to calculate the work done by tension force, of course you have a tension here this way. But here your tension is up. Concentrate on tension only here. We're not talking about the other forces. Now let's say this system, definitely this system will go down, yes? No other forces this way. So when this object moves from here to there, this is the displacement, yeah? Delta R. What happens to this? Start initially here, finally where? Same delta X or different? Or delta R? If this one comes down 1 meter, this will move 1? Same. FT here and FT here are different or the same? Okay, now, do you need to calculate the work done by tension force here? The answer is no. Why no? How much is the work done by tension force here? Is Ft multiplied by delta R cosine what? 0, which is 1. So what's the answer here? W is Ft delta R, yeah? Cosine 0 is 1. Here, which way is moving? Tension. What's the angle? So what's the work here? Minus Ft delta R. What's the total work done by tension now? 0. So if you have cable connecting two masses, don't calculate the work done by tension because cancel each other. Okay? But if you have one cable, no, you're pulling, no, that's an applied force. You have work. So this is the story of conservative and non-conservative. Now we move to another part. Potential energy, U. Potential energy, U. Please stick to the symbols I use, because I know some of you learned potential energy and used P dot E. Use U, not P dot E. No. What is potential energy? Let me write a definition to make it easy, and then we discuss it rather than. So I'll just write a definition here for potential energy. Potential energy, it is the energy that can be associated with the configuration or arrangement of a system of objects that exert force on one another. Right, I'll read it for you. Potential energy is the energy that can be associated with the configuration or arrangement of a system of objects that exert force on one another. This is a definition, but let's discuss what does it mean. If you remember, so far we talked about work and kinetic energy. But in the beginning, I told you that there are two types of energies: mechanical, kinetic, and potential. This is the second one, potential energy. What is this energy? I know kinetic energy is energy to do with motion. When an object moves, it has kinetic energy. But what is this energy? This energy, from the definition, to have it, you have to have two things. You have to have an arrangement of object mean masses, number one. But this is not enough. Condition number two, force exerted between the objects, yes, among the objects. So whenever you have a system of masses, objects, definitely you have forces among them. Why? Because when you have masses, you have a gravity force. One of the laws. So if you have an arrangement of masses, when we say an arrangement, can we have an arrangement with one mass? No, one mass.
No.
So when we say system of arrangement, at least, so two and above. Which means now when you talk about potential energy, you cannot talk about a potential energy of an object, because object means one. It's wrong to say what is the potential energy of the pen. What is the potential energy of the chair? Wrong, because you're saying one object, yes? Potential energy needs at least an arrangement of two objects. Now back to the definition. The definition says if you have an arrangement of objects, and among these objects there are forces exerted, then you have potential energy. Let me give you an arrangement. Two pens. Arrangement or not?
Arrangement.
Is there a force or not
There's a force.
between these pens? Yeah? Gravity. Of course, you don't feel it now. You can't see it because it's very small and there are other forces much stronger. I'm holding them. But if I take the pens to space and I go away, what happens? Move towards each other. Yeah? So the arrangement will change. Now, the natural question is that when the pens moves, it means I have kinetic energy, yes? Where does this energy came from? I just put the pens at this distance. Why they move towards each other? Where does this energy came from? You all know that we cannot create energy. Can we? So it must be there, but we convert it from one shape to. So here, when I take those two pens to space and remove my hands, what do I see? They start moving. So it means I have kinetic. Where does this energy came from? It must have been somewhere. Outside or inside? The system, because no effect from outside, yeah? This energy, which was inside, we call it? And there is another way, you say potential energy, think of it as a stored energy, stored in the system. Now, when you have something stored, do you have a feel for it? Can you feel it? No. When you have a feeling for it, when you change it, spend it. Like, we always, we have this analogy. We always think of potential energy as your deposit in the bank. Let's say you have 1 million dirhams deposit in the bank, yeah? She's laughing. 1 million dirham in the bank. This 1 million, is it in your hand? No. Do you feel it? No. It's just a number in the statement, yes? When do you have a feeling for it? When you go and cash it. Start moving. Spending, yes? So anything is stored, usually it's not, you don't have a good feeling for it, yes? You have to cash it too. Potential energy like that. It's an energy there in the system, but you can't say it's there or there. It's in the system, but the moment you want it, cash it. How you cash it? Change it to another type. Like this, the pens. Do I have potential energy? Yeah. How do I know? Give it the freedom. Move your hands. They start moving. Oh, so there was energy inside. Convert it to motion. This is how potential energy works. You now have potential energy. Your system in the classroom. Mass number 1, mass number 2, mass number 3, mass number 30, yes? Now, do we have an arrangement? Yes. She is at a distance of 70 centimeters. She is at a distance of 5 meters from the students in the corner. You with her 3 meters. So on, yes? Now, this system has potential energy, yes? Where is it? Show me. You have a feeling for it? No. But I'm sure it's there. What's the proof? Now, if I take you as you are now to space without your chairs, you can take your chairs with you, no problem. Just imagine now you are in space. Suddenly you are in space, as you are. No other forces, nothing surrounding. What happens to you? You start moving, pile up. Where does this energy came from? It was not moving, yes? So it must have been stored in the arrangement. Now it shows as kinetic, yeah? So potential energy is like that. Something you have, it's in your pocket. You can't see it, yeah? You can't feel it. When you feel it, and you pull it out of your hand, cash it. Spend it. Now, because we are living on Earth, so we take our system, our arrangement of two objects, yes? The first object is the Earth, always. The second object is any object you want. So if I say I'm talking about the pen, it means I'm talking about the system pen, Earth. Everything relative to Earth, yes? So now I have a system of two objects. Now, pen, Earth, now, at the moment, does it have a potential energy? Yes. Why? Because there is an arrangement. This pen at a distance of 2 meters from the ground. If I change the arrangement, what happens to the potential energy? Changes as well. Whenever you change the arrangement, which means the spacing, the distances, you're changing the potential energy of the system. All right? I hope this is clear for potential energy. So I don't want you to think like what you learned in school. Potential energy is mgh. You remember mgh? H is height. Height because you are talking relative to the ground and everything is above ground. But think in space. You have Earth and pen. What do you have now? Arrangement. You call this H, yes, because you look up. But from space, this is not H. The spacing, the arrangement. Now take the pen to this point here. You change the arrangement, new arrangement. When the pen falls, you change the arrangement. Okay? But this arrangement here on Earth, we call it H, because you're always going up, down the ground. Now, potential energy is divided into two parts. We have two types of potential energy. We have potential energy, first part, is to do with what I've been explaining just now, with the gravity. The force, what's the force of? Gravity. So we call it the gravitational potential energy. The second part, of course, here you give it the symbol U sub G, gravitational potential energy, U sub G. The second type of potential energy is nothing to do with the gravity. It's to do with changing, deforming the arrangement of a shape. We call it elastic potential energy. U sub S, because elastic is like spring. Okay? Now, the first one, I already explained it. Gravity between Earth and the ground. This is an arrangement. If you take the pen up, you're changing the arrangement, you're changing the potential energy. Down, up, and down. Elastic. This is nothing to do with going up and down. This is to do with a spring. So if I have a spring, at the moment, the spring has an arrangement, yeah? The rings. Think of the rings not as rings, think of them as points. So this is a point, this is a point, this is a point. Each point is what? It's a mass, small mass, yes? Do I have an arrangement of masses or not? Points, yes? When you pull the spring, what happens to this arrangement? Changes. So what you'll have now, so if you follow this point and this point, these two, here, you change the arrangement. Any two you take, yeah? Okay? That's number one, arrangement. Number two, you need force. What sort of force do you have in the spring? Spring force, yes? Fs. So now, do I have two conditions or not? Arrangement and force exerted. So do I have potential energy? What shall I call it? Elastic potential energy. Now, you all know and experience this. When you pull a spring, what do you feel that? The spring has energy stored in it, yes? This is potential energy, elastic. Why? Because when you remove your hand, okay, so there was energy stored in it, and now it's been converted to motion. So this is elastic potential energy. Right. Now, what is next? I need equation to calculate the gravitational potential energy and elastic potential energy. Let's start with the gravitational potential energy. U sub G. I'll just go quickly on this part because I need the equations only. let's say this is Earth, the ground, which is Earth, yeah? Object number 1. And here at this level, initial level, I have an object, mass, pen, the pen. Now think of it like this here. This is the pen. Okay? Where is the ground there? So what's the arrangement? Ground, pen. At a distance of, let's say, 1 meter. Yes? But let's call it Y1 or YI. This arrangement, does it have potential energy or not? Yes, yes, because there is a force of gravity between the pen and Earth, and I have an arrangement between the pen and Earth at YI. So there is an energy stored now in this system. If the pen, somehow, we move it from initial to final level here above or below, it doesn't matter. What happens to the arrangement? Changed, yes? To a new arrangement. Y final. This is the pen. Gravity is this way, yeah? So I have a force of gravity, and I have an arrangement, so there's a new potential. So let's call the one potential energy here for the system initial potential energy, UI. Here, UF. So what happens from here to there? You have delta U for gravity. U final minus U initial. Now, this is the pen here. Initial. I take it finally here. What happens? The arrangement has changed. So the potential energy of the system pen Earth has changed. If I touch the pen like that, the pen falls. Why? Yeah, but think energy concepts here. What did you have here? What did you have? Stored energy. Potential. Potential to, remember when you say someone has potential, it means you have the ability to do something. There was an ability here, yes? Energy, but it's inside you. When it shows, when you have the freedom, yeah? Okay. So I gave it the freedom, it shows. Shows at what? Kinetic. So here, the potential which I had here and the potential I had here, are they the same? No. Which one do you think it's higher? When the went with a bigger arrangement, yeah? Here, because here when it falls, the speed doesn't go as much as high as the one from the top. So the higher you get, you are increasing what? Potential, okay? But here, when you go up, you go against gravity or with the gravity? So the who is losing? No, but when you go up, increases. So when energy increases in one part, you must decrease. Where is the decrease here? In the work of gravity. You're going against the gravity. When you go up, you have to lift, yes? So you have to give energy. The energy you gave to lift it, where did it go? It's stored as potential. Okay? When it comes down, you return it. You take it back. So you can store energy this way. Like if you have water, take it up and then release it. When it comes down, it has kinetic. And if we put a turbine, the turbine will start rotating, and then we can generate electricity. But this is not a good way of generating it, because you took the water up. This is energy as well. But if it happens naturally, you have water on top of the mountain, just release it, but control it and put a turbine, hydraulics, yeah? Then you generate electricity for free. It's not free, of course, But God, he took the water for you, not you, lifting all this water and put it on top of the mountain by evaporations. Yeah? So nature itself, it has energy, but it converted from one type to another using potential energy. Think of potential energy. It's a useful concept. So now you can see that the gravitational potential energy is to do with the gravity work as well. And how you find the gravity work is Fg delta y, yes? And cosine the angle. But here, remember the angle. Sometimes you go up, sometimes you come down. But all what I know that when U increases, the gravity negative. When this one decreases, gravity. So we can conclude this, that the change in the gravitational potential energy is equal to the negative of the work of gravity. When this one loses, this one, when this one gains, that's why you need the minus. They work opposite. The minus is not direction here. Increase and decrease. And this change happens because of gravity work. All right? Now, delta U gravity, or here, sorry, W Fg, it's mg, yes? Delta y. Now, ignore this part now because it's sometimes positive. Mg and delta y. Y final minus y initial. So if I open this one, I'll have mg y final minus mgy initial. This is the work of gravity. But what we said, work of gravity, so it's the same. So I can say now delta U is U final minus, and each U, you can see each U is equivalent to mgy. But final and, so delta U is mgy final minus mgy initial. This is delta U of gravity. This is the change in the potential energy. Now, listen here. There's a difference between the question, what is the potential energy and what is the change in potential energy? When I say what is the change in potential energy, I mean delta U. But if we say what's the potential energy, we mean at a level. What's the potential energy here? What's the potential energy here? So we mean U, not delta U. And U, you can find it by mg, the position, vertical, y. How do you find y? And how do you find y? What is y? But relative to a reference. Y here, relative to a reference. So it's very important when you talk about potential energy, think of references. Where is your zero potential energy? Okay? So this is potential energy equation of gravity. Now, let's use the same concept now and talk about the second potential energy, which is the spring. Gravitation, elastic potential energy. Now, just before I move to this one, now what you have to remember now for potential energy, delta U gravity is equal to negative of work of gravity. And you know how to calculate work of gravity. Delta U means U final minus, and delta U, mg y final minus mg. Remember the y final, y initial, those are height relative to a reference, 0 y. Where is the 0 y? Not necessarily on the ground. You choose it. It's a level. I can put the reference here. So how much is yi? 0. You are on the reference. But if I put it here, this is yi. If I put it here, this will be yi. Like the ruler, where you put the 0, then you measure from the 0, yeah? But the best way is this. This is very important. The best way is that always put the reference at the lowest point. Why? Because then you have every y positive. If you have the reference above, you'll have negative y's. Okay? So now, elastic potential energy, U sub S. We'll use the same argument. In gravity, didn't we say delta U is minus work? Now here, think of this equation for a spring. The change in the elastic potential energy of a spring is equal to negative work of the spring. Now, what is the work of a spring? Half kappa x initial square of the spring minus half kappa x final square of the spring, yes? Now, substitute here. What you'll have? Delta US minus half kappa x initial square minus half kappa x final square. When you multiply by minus, the I become negative, the F becomes, so put the positive first, negative. So you'll have delta U spring half kappa x final square minus half kappa x initial square. Now, what does delta U means? U final minus? So can't I say this is U final? And this is U initial, and this is delta US? And this will lead me to the conclusion that U for a spring is half kappa x square at the position of the spring. What is x? What is x? It's the position of the spring relative to the equilibrium, 0, not stretched, not compressed. So if you're pulling the spring, this is the x, yeah? Positive. If you compress it, negative. But relative to the 0. 0 it means when it's not compressed or stretched. 0 for the ruler. So that's it. This is potential energy, both elastic and gravitational. We'll come back to solve this question. I want to move to another title before it's too late. Power, P. What is power? First, power is not force. Power is not work. Because if power is force, why we call it power? Call it force. Yes? So one of the misconceptions here that you think power, if someone is powerful, it means more force. Power is a concept, yeah? Different from force. So power is not force, and power is not work, because it's work, so call it work. Why call it power? So what is power? Power is a concept introduced in physics because if I have, like, I ask two of you to do work for me, like this chair, I asked Lina to push this chair with a force of 10 Newton only to a distance of 10 meters this way. Okay, so think there. This is chair number 1, or student number 1. She is pushing with F equal 10 Newton to a distance of 10 meters. How much is the work done by these students? 10 times 10 cosine 0. 100 joules. This is the work done by Lina. Okay? Now if we ask Dana, yes? I'll tell her, come and push this chair with 10 Newton, 10 meters. Same chair. But remember, this is students number 2. How much is the work done by students number 2? 10 cosine 0, yeah? Which is 100 joules. Okay, you might laugh at this. So what, of course, it's obvious, yeah? That's what you thought. Okay. Both of them, they did the same work or not? They work for me, yes? I'm the boss. I asked them to do this. At the end of the day, they both did the same job for me. What I have to do, I have to pay them money. Shall I pay them the same amount?
No.
Why not?
No, the same word. Depends on the time.
That's good, very good. How do I distinguish between what the first one did and the second one? Both they did the same job, but one of them finished the job in a shorter time, yes? So once you want to distinguish between works, they have the same weight, what you have to do, you have to divide it by the time taking, then it becomes power. So power is the rate of doing work, is not work. The rate of doing work. Yeah? So if you have 2 machines, they do the same job for you, yes, same work. How you distinguish between those 2 machines? You see which one can do the same job faster. Faster doesn't mean the speed, faster time, shorter time, yeah? So according to this definition, what is power? Work over time. So P power is work over time. And don't forget, work, it's a transfer of energy. So it's energy over time. What's the unit? Joule per second. Now, P equal W over T. Time is delta T, remember, start and finish, yeah? Now, when you have a start and finish, the time is not short. So when you say power, you mean average power. Because start, finish. So this is P average, AV. Now, work, what is work? Force dot displacement. So now substitute. P equal F vector dot delta R over delta T. Now, what is delta R over delta T? Displacement over time. Average velocity, not velocity. So what is power average equal to? Force dot average velocity vector. Yes? Average velocity. And this is dot. So to find power, what do you need? Force and velocity. If it's power average, you need velocity average. If it's power instantaneous, you need instantaneous velocity. Now, what is the other way to find power average? F magnitude, average velocity magnitude, cosine the angle between them. Be careful, this angle between velocity and force, not between velocity and displacement. This is not work. Between F and V average. So this is average power. Write the title, average power. Now, what if I want instantaneous power? What does it mean instantaneous power? It means, this is the question, what is the power at 3 seconds? What's the power at 4 seconds? At 0, 1 time, not from 2. So if you want the instantaneous power, what you have to do, if you have average, take the limit. Remember, if I take limit, delta T approaches 0 of average power, it means I'm taking the limit, delta T approaches 0 of F dot delta R over delta T. Okay? Limit of average becomes instantaneous. So power instantaneous equal. The limit goes for the F or for the delta R over delta T?
Delta R.
Because the time is here. So F is out. So you have F dot limit delta T approaches 0, delta R, delta T. What's the limit of delta R over delta T? This is average velocity, yes? When you take the limit, it becomes instantaneous velocity. So P average, P instantaneous is F dot V instantaneous vector. And if you want the magnitude, P instantaneous, F magnitude, V instantaneous magnitude, cosine the angle between them. So this is how you calculate power. And remember, the unit of power is joule per second. Joule per second is watt. We have watt, kilowatt, megawatt, gigawatt. Now let's put the last title. Yeah. Conservation of mechanical energy, E. Conservation of mechanical energy, E. How many types of energies do we have so far? Two. Potential and kinetic energy and U potential. Now, if you have a mechanical system, not electric, mechanical, not chemical. In a mechanical system, when you add the kinetic energy to the potential energy, we call it mechanical energy, total energy. So here how we define it. Could you close the door? E, mechanical. And E is equal U plus K, always. Mechanical energy equal kinetic energy plus potential energy. Now, here we want to talk about the conservation of mechanical energy, which means the mechanical energy is conserved. It doesn't change, increase, decrease, but goes back to original value. Now, think of a conservative system now. Not conservative force, conservative system. So I'll talk about conservative systems. Conservative system. When do we have a conservative system? When you read the problems, when you want to solve a problem in physics, what you do first, you read it, yes? Now you have to decide, is the system you have conservative system or non? How you decide? If the system is conservative, it means you don't have non-conservative forces in it. So when you have a conservative system, it means the system has force of gravity or force of the string or both. No other. No friction, no applied forces. So if you read a question and say frictionless, no applied forces, what is the system? If there is a friction, if there's applied force, and if both, yes. And one of them can ruin it. So if I have a spring and friction with it, so you could have not conservative, okay? Now, when the system is conservative, it means that E doesn't change. Your credit doesn't change. So let's say your system is here initially. What you have initially, you have potential energy initial and kinetic energy initial. If I add them, mechanical energy initial. And what do I write here? E initial equal UI plus Ki. Now, if the system changed to a final state, not like you're moving, like you have state. Initial state, final state of the system. What do I have finally? I have final kinetic, final potential. If I add them, final mechanical. Now, this is general. Huh? If the system is conservative, does EI and EF will be different? Or they? So in conservative system, initial mechanical must equal final mechanical, yes? Which means delta E, 0. No loss, no gain of energy. So what's the formula now? EI equal EF. So I say UI plus KI must equal UF plus KF. This is the formula used for conservative forces, for conservative system. What do you put instead of UI? If it's a gravity, what do you put? MGYI. If it's a spring, half kappa x initial square. This is for U. Plus kinetic initial, half mv square initial only, yes? U final, mgy final, if it's a gravity, or if it's a spring, half kappa x final square. Plus half, okay? That's it. Read the system. If it's conservative, this is your formula, substitute. Now, what if your system is non-conservative? What does that mean? We have friction or applied force or both, yeah? So in this case, if the system here initially and here is finally, here we have UI, KI. You add them, it gives you EI. Here UF, KF. You add them, it gives you EF. In this system, is EI and EF are equal?
No.
So here what you have, EI is not equal to EF. So if they are not equal, what does that mean? I'm sorry, I'll just take 5 minutes more to finish this one. So what we have here, we have EI is not equal to EF, which means EF minus EI equal delta E, and is not equal to 0. If it's not equal to 0, it means you are losing or gaining energy, non-conservative. Gain and loss. So how much do you lose? How much do you gain?
0.
It's a number. No, non-zero. Delta E is not 0. Here, delta E is 0. So how much did you lose? How much did you gain? That depends on friction force work and applied force work. So to find delta E is always equal the work of friction. This is how much you lost, plus the work of the applied force. This is how much you gain or you lost, depends on the angle. You add those two, it tells you the difference. Maybe you have a profit or loss, yes? How do you calculate WFR? Minus FR delta X, and the minus is for 180. Applied force, FA delta X cosine theta. I don't know what's the angle. This is how we calculate delta E, okay? Now, EI is not equal to EF, so delta E is not equal to 0, equal to this. Let's substitute now. EF minus EI equal delta E. What is EF? KF plus UF minus EI, KI plus, no, not minus, UI equal delta E. Now, when you open the minus here, bracket, what you'll have? KF minus UF minus. So you'll end up with you say K final minus K initial plus U final minus equal delta E. What is K? This one? Delta K plus delta U equal what is this equation for? Non-conservative system. So if you have a non-conservative system, this is your equation. If you have a conservative system, this is your equation. How do you use this equation? Break it to pieces. What is K final? Half mv square final, yes? Minus half mv square initial. Plus, what is U final? Either mgy final or half kappa x square final. Minus either mgy initial or half kappa x initial square. Equal delta E. Okay, minus FR delta X plus F delta X cosine theta. Remember, you don't have to write this equation. This is how you do it. What you have to remember now, you have two systems. If the system is conservative, this is your equation. If the system is non-conservative, this is your equation. But how you apply them, open them up, yes? Okay? You got it? Yes. This is chapter 8, finished. Finished. Okay, thank you. Finished.